Hey guys, hope all is well with everyone. So in this video we're going to be continuing with part 2 of the elephant toothpaste experiment series, and what we talked about last time is when we saw the foam effect from the experiment, we concluded that the hydrogen peroxide basically was undergoing a decomposition reaction. We talked about how hydrogen peroxide is extremely unstable. It wants to constantly break down into its more stable molecules, being oxygen and water. And then what we saw was the foam effect was created by when the oxygen product was formed, it was trapped by the Dawn dish soap. We talked about how dish soap or liquid detergent is very cohesive. It sticks to stuff. So it basically trapped and created a foam-like effect. But we also talked about what the yeast was in terms of the reaction, and we determined it was a catalyst. So it decreased the energy of activation required, or the activation energy needed for the reaction to come to fruition. So what would take a couple of days for this reaction to take place was only a matter of seconds. So we talked about what a catalyst was and how it took its role. And one of the things we didn't really talk about is a catalyst is in the reaction, but it doesn't really take part in the reaction, but it still speeds it up. And we'll kind of talk about more about that aspect as we go into this high school version of the elephant toothpaste experiment. So what you see in front of you is 3 vessels that I have added different kind of components to, but the reason I want to do this is I want to kind of take our experiment from last time and compare it to the parameters that we're going to change to this version. Now, one of the reasons I want to do that is because in the concept that we're going to talk about, we're going to talk a little bit about how we balance equations, we're going to talk about kind of some stoichiometry, and we're going to talk about how different factors, things that we can change to the reactants or an experiment, changes its effect. So I'm kind of creating kind of a comparison or multi-comparison analysis in this part 2 of the video. So what I'm going to do is I'm going to start off by talking about all the supplies that you're going to need. That includes the ones from last time, and then the ones that we're going to go into adding on with changing some of the things with this experiment. I will say that as we continue to go forward in this experiment, things can get a little bit more expensive. A lot of the things that I'm going to be using are from like chemistry websites, and some of the chemicals that I get are not just on your ordinary Amazon website or anything like that. So again, things can get a little bit more pricey as we continue to intensify the experiment a little bit. But what we'll do to start things off is I'm going to kind of explain what I have in front of me, but we'll go through the supplies first. So as always, we have our hydrogen peroxide. The last time we talked about was the 3%. In this version, we are also going to be using this 40 volume clear stabilized formula. You can get these at like hair salon stores or anything like that. A lot of hair care products contain hydrogen peroxide. This is the equivalent of 6% hydrogen peroxide, so it's basically double the concentration of what we were looking at last time. So we're going to see if that definitely is a factor in terms of the result of the reaction taking place. We're still going to be using our yeast. Remember, it does need to be active dry yeast. You can find it in the baking section of the grocery store. And again, you can find them in these nice packets of 3. Because this is a comparison analysis, it is nice to use 3 different colors of food coloring, just so you can kind of see the different effects and for a little bit more vibrance. You're still going to want a funnel, and again, we have that hack that if you don't have a funnel, you can use the trick of taking one piece of paper and going across to the opposite corner to make that conical shaped piece of paper where you're able to keep your reactants contained into the vessel that you want. The other thing is that you may want to use gloves and goggles for this. We are increasing the concentration of the hydrogen peroxide. This stuff is a little bit more concentrated than the stuff that you would put on your cuts and scrapes. I'm not going to be using gloves, but I will be using some goggles here just for really emphasizing safety. And then you're going to want some water, again for your reaction and your solution of water and active dry yeast. Then the other thing that we're going to be introducing in this experiment is going to be another catalyst that we talk about, but this one is known as potassium iodide. It is another type of catalyst. Again, this stuff isn't very cheap, but again, it's really fun to introduce to this aspect of the experiment and seeing how it differs from other catalysts like the yeast. So we'll take a look at that, and then some other optional things are some scissors for opening the active dry yeast, and I think that pretty much covers it. You might also want a spoon for stirring, and again, I'm going to be using my magnetic stirrer here. But let's go ahead and get started. So the first thing that we did last time was we introduced the hydrogen peroxide. This time I'm going to be using Erlenmeyer flasks, and what I want to show you with these is from your left to right. In this vessel I have 80 milliliters of the 3% hydrogen peroxide solution. So that was what we did last time, and we're going to be adding the dry yeast to this guy. And then in this one and this one, I have the 6% or 40 volume hydrogen peroxide. So these are twice the concentration as this one over here on the left. So then what we're going to do is we're going to go ahead and add our liquid detergent, or liquid dishwashing liquid, to all three of the vessels. And again, remember from last time we talked about how the dishwashing liquid, it's not so much the volume that is important as what it's physically doing as part of the experiment. So remember, as I mentioned, if you try to put it on a tablespoon to measure out the 1 tablespoon that you need, what's really going to happen is most of it's going to stick to the spoon. So you can eyeball it and it won't have a drastic like setback on your experiment, okay? So what we have here in front of us is the hydrogen peroxide solutions with dishwashing liquid, and then let's go ahead and add our food coloring. So for our 3% hydrogen peroxide, we'll use green. So this is going to be the 3% hydrogen peroxide and water yeast solution. And then in the middle one, this is going to be our 6% 40 volume hydrogen peroxide and potassium iodide solution. Okay. And then in our last one, we have the 40 volume. Oh, okay. Made a mistake there. Hold on. Sorry about that. This is going to be the 3% hydrogen peroxide solution with the active dry yeast. This one is going to be the 40 volume hydrogen peroxide with the active dry yeast, and this one is going to be the 40 volume solution of hydrogen peroxide with the potassium iodide catalyst. Okay, so what I'm going to go do is go grab some hot water so we can put our two water yeast solutions and prepare those. And then what we'll do when we come back is we'll do a comparison analysis of the three and see them in action. So I will be right back. I'm just going to go get myself some hot water real quick, and I shall return. Alright guys, so we are back with our hot water here. So what I'm going to do is I'm going to go ahead and start with the stirrer. And we're going to add, so what I'm going to do is I'm going to be adding 2 packets of yeast here because I'm doing 2 basic experiments. So again, what you're looking for with this is you want it to be as least viscous as possible. So you kind of want to terminate the addition of the yeast before it starts to get really pasty and putty-like. So I'm going to keep adding here, but I did double the amount of water to kind of keep the solution uniform. So not sure. And just as a friendly reminder, this stuff doesn't really smell the greatest. Okay. So there's a little bit of a clumpiness going on here. I want to see if we can remedy that. good. It does kind of have like a putty-like consistency, but I'm not going to use the entire thing. So what I'm going to do is add 20 mils to this guy, add 20 mils to this guy. We can probably go to 30 and we should be good. And as we continue to talk about this experiment as well, we're going to notice that the addition of a catalyst is only beneficial to a particular point. So we'll keep going with that. So what we're going to do now is go ahead and add our three things. I'm going to try to add them as quick and instantaneously together as possible. So just as a quick recap, your solution here is 3% hydrogen peroxide, which is going to be added with yeast and water solution. This one is going to be the 40% 40 volume, 6% concentration of hydrogen peroxide with yeast and water. And then this guy's going to be the 40 volume, 6% hydrogen peroxide with potassium iodide. So let's go ahead and see what happens. I'm going to try to do this as quickly and instantaneously as I can. So on the count of 3, I'll add these. 1, 2, 3. And then this guy's kind of on a delay. Interesting. There we go. Well, as you guys can see, the middle guy, oh, there we go. So it's kind of slow, but interesting. This one's happening extremely fast, so it's kind of cool to see how fast the bubbles are being made. But as you guys can see, the middle one probably had the biggest reaction, which was actually with the yeast, which is kind of interesting. But as you guys can see, the foam is definitely being created here as a product. And yeah, this guy's, let me see if I can kind of zoom in here. So the guy on the right, or yeah, on your guys' is right, still kind of going to town here. He's, you can kind of see the bubbles. But yeah, so from a volume kind of perspective, the right one actually made a lot of foam. It just took a while to get the reaction started. But so this is kind of phase 2, guys. So we kind of see a lot of differences in our reaction here. So, and again, it kind of goes to the parameters that we've changed about it. So what we're going to do is we're going to go ahead and look at this in an in-depth discussion. This one's going pretty crazy here, but we're going to go into an in-depth discussion of what's happening from a molecular and chemical level to see why this is happening in comparison to this guy over here from our previous experiment. So I'll see you guys there shortly. Hey guys, hoping all is well. So welcome back. We're going to be taking a look at the overall kind of effect here of our reaction. So you guys can kind of see how the bubbles have kind of dissipated, so it's kind of just starting to settle. But I wanted to go ahead and talk about kind of an in-depth discussion, but we're going to kind of go a little bit more into some more advanced topics here, building upon what we learned from our first experiment. So the first thing that we'll take a look at is what we didn't talk about last time is balancing of equations. So normally this is a decomposition of hydrogen peroxide into water and oxygen, but last time we didn't have it balanced. So remember, with the stoichiometric coefficients, you want to be able to optimize the balancing of the equation so that all of the elements and the total number of atoms that they have are balanced on both sides. So what we need to do here that we didn't do last time is put a coefficient in front of the hydrogen peroxide and put a coefficient of 2 in front of water. This is going to give us a total of 4 hydrogen atoms. 4 hydrogen atoms. 2 times 2 is 4 oxygen atoms. 2 times 1 is 2 oxygen atoms. And 2 times 2 is 4 oxygen atoms. So let me see. Oh, I'm sorry. Hold on. 2 times 1 is 2 plus 2 is 4. There we go. Sorry about that. So let's talk about, again, going into a build on that, why is hydrogen peroxide so unstable that it is? Well, there's a couple things. So looking at the Lewis dot structure that we have here, and another way to look at it here, you have two things that you can consider. Its molecular geometry is bent, and its electron geometry is tetrahedral. But the biggest thing about it is this third oxygen. Because oxygen is so small in terms of atomic radius and atomic mass, it's going to have to choose between one of the two atoms it's bonded with to bond tightly to, and the other one's going to be very loose. So the overall presence of a second oxygen atom compared to water is what makes this highly unstable and wants it to be able to bond to something so quickly. You have bond lengths of hydrogen bonding and oxygen bonds in like the picometers, which is like 10 to the negative 13th. So you're looking at very, very small bond lengths here, which again, because of the non-tightness of one and an extreme tightness of the other, the oxygen atom is going to cause the desire for hydrogen peroxide to bond so quickly. Now, one of the other things that we can look at is potassium iodide. So again, potassium iodide is another catalyst that we used instead of yeast, and as you can see, they kind of had an interesting effect. Normally, when you add hydrogen peroxide in an environment with potassium iodide, the reaction is pretty instantaneous. As you can see, once I added mine, there was kind of a delay. It could have been the amount that I added in comparison to the amount of hydrogen peroxide that I had. But once it started, it was going for quite a while, and the bubbles that were forming were very quick. So once it started, it was going like the Energizer Bunny, so to speak. So kind of comparing potassium iodide and yeast to the comparisons, they're both excellent catalysts. One of the things that I like to mention is potassium iodide is just more uniform. So when you're creating your active dry yeast and your water solution, you don't have a completely uniform solution. It's not all like completely 100% uniform throughout the entire solution. Some physical states of matter of clumps of active dry yeast may be present in other parts, so it's not like a completely physical state of matter of a liquid like potassium iodide is. So speaking of that, we can look into the factors that affect a reaction, not necessarily speed up, but affect a reaction. So one of the factors is the reactant concentration, which we definitely saw. You saw that there were much more of a quicker result of the red foam, and when we look at concentration, we're looking essentially at how much of something is in per unit volume. So 3% is going to be half as much hydrogen peroxide than 6%. So doubling its concentration to 6% is going to give us quite a drastic effect, especially at a small concentration like that. Temperature is another one, along with pressure. So in this room, obviously, we're kind of at STP conditions. We're just at standard temperature and pressure. So not much there, but the presence of a catalyst definitely affected the reaction, as you guys can see from the three vessels. Definitely, again, is going to speed up from a reaction that would take days to the second or instantaneous reaction that we saw. Another thing that we're going to kind of look at here is you're kind of looking at the instability again. The three bonds that hydrogen peroxide has, you're looking at a single oxygen-oxygen bond, and then you're looking at two other hydrogen-oxygen bonds. So we talked about why oxygen is so small. It has to choose between tightly bonding to one atom and then loosely bonding to another. This last thing here is talking about its thermodynamics. So when we look at this, we're basically looking at the overall reaction from kind of an ionic state of reaction. So you have hydrogen peroxide plus the iodine ion is going to yield water and the iodine oxide ion. And then this is basically using Hess's law, which is kind of just a series of reactions that add up to your final
results that you get. You get the oxygen that is released, but then again, we are using the dish soap to contain it. So we get the foam that we do down here. Your delta H is going to be negative 196 kilojoules. So remember, when something that is delta H is negative, that's automatically going to result in a exothermic reaction because heat is being released into the environment. If it was endothermic, it would be positive, which would mean that it would feel cooler, or the surrounding area would feel colder to the touch or feel. Okay, but I hope you guys enjoyed this video. In our next video, we are going to be kind of amping up the experiment one last time, and we'll be talking about a couple other things. But I hope you guys enjoyed this. If you liked the video, please don't hesitate to like and subscribe. And again, if you guys have any requests for any videos or experiments, I'd be happy to show them to you. But as always, guys, please take good care and be safe, and we'll see you soon.